Okay, so welcome back once again. And in today's module, let us understand the concept of multi-bit binary additions. So you have n-bit numbers in binary. That number could be 4 bits, 8 bits, 16 bits, 32 bits, and so on. And you got to understand how the binary addition will be performed. So let us say this is that number A, where you see this is an n-bit number starting with the least significant bit LSB A0, A1, A2, A3 to the AN minus 1 and finally the MSB, most significant bit AN. So this is an n-bit number. This is another n-bit number, let's say number B. The word size of number B is again n-bit, starting from LSB B0, B1, B2, B3 up to Bn, with Bn representing the most significant bit, MSB. Now, we want to add these two numbers. As I said, the n bit could be any word size starting from 4 bit up to 256 and so on and so forth. So the addition of these two numbers will give us the result called sum. That could be expressed as S0, S1 up to Sn. S0 being the LSB least significant bit and Sn is the most significant bit. So addition or sum of A0 and B0, 1 bit each, gives you 1 bit S0. 1 bit of A1 and B1 gives you sum of S1 and so on. Now, there is a concept called carry starting from again C0 representing LSB up to Cn in the n-bit binary addition. So to understand this, initial carry bit, that is the C0, is right over here. It could be a single bit representing logic 0 or logic 1 that gets added to the sum of A0 and B0. So if the initial carry is present, the total sum will be A0, B0 and C0. Finally gives you sum S0. If this addition right here of A0 and B0 generates a carry, that comes as a C1 right here, that gets added with the sum of A1 and B1, giving you again sum called S1. If this addition right over here generates a carry, that is represented by C2, that gets added with A2 and B2, finally giving you a 3 bits addition represented by S2. Again, if this addition at this stage generates a carry, that comes here as C3, that gets added with A3 and B3, gives you a final sum called S3. So this process one by one continues. It is continued until the final addition of Cn, An, Bn, giving you a final sum called Sn. If the final MSB, most significant addition of the bits, generates a carry again, that is represented as overflow, or that is left as it is. And that carry bits taken into account to finally represent the final sum of the n-bit number. So let us understand this with an example. So let's say I have an 8-bit number. Why 8-bit? Because it starts from A0 up to A7. You see all bits, A7 being the MSB, A0 being the LSB. And that number is 00101010. So if we see that each 4 bits of this number split it into two 4 bits, so number is 00101010. In decimal, it is equivalent to 42. Let's say I have another number B. with word size of 8 bits, starting with B0 up to B7. B0 being the LSB, which is bit 1, and B7 being the MSB bit 1. And we read this number right from the left one, 1110, 1001. In decimal, this number is 233, and we are going to add these two numbers. So we know that 233 plus 42 is equal to, in decimal, we know what is the addition. It is going to be 275. So we'll see how this addition in binary will now take place. So this is the number again, 42, 0010, 1010. Then I have to add here another number we just saw called 233, which is 1110, 1001. So I start with the LSB of number A and number B. That is, I want to add 0 and 1. Here, I don't have any initial carry. So when I'm adding these two numbers, I assume that the initial carry here is 0. That is, C0 is 0. Now, 0 plus 0 plus 1 gives me binary sum of 1, and it generates no carry. That's why the carry here is 0. Now 0 plus 1 plus 0 in binary, I get a sum of 1. Again, it generates no carry. Therefore, the carry here is 0. 0 plus 0 plus 0, the sum is 0 and the carry is 0. So here 0 plus 1 plus 1. So addition of these three is in binary 1 plus 1. The sum is 0 and it generates a carry. That is how we write here. And we see that now 1 plus 0 plus 0. The sum here is 1 and it generates no carry. Therefore, carry here is 0. And here 1 plus 1. Sum is 0 in binary, but it generates a carry that is 1. Again, 1 plus 1. Sum will be 0 and it generates a carry here. Then 1 plus 1. Again, the sum is 0 and now the carry gets generated, but it doesn't have any bits from number A or B, so it stays as it is. Finally, this carry is put in front of the MSB of the final sum number, and the total number is now counted as or seen as 1 0 0 0 1 0 0 1 1. So it is a 9-bit number that is representing in decimal to be 275. So here it is, we see that the addition of the n-bit numbers are done and binary addition of 8-bit numbers as an example is given. Let's have another example of this binary addition. So I have now 4-bit number A, 0011. It is in decimal number 3. I have another number B, 0101. It is in decimal to be equivalent to 5. I know that the addition of decimal 3 plus 5 is the result called 8. But now in a binary, what I see here, the LSB of both A and B is kept right over here. So from number A, the LSB is 1. From number B, the LSB is 1. And addition of these two LSBs, 1 plus 1 in binary, sum is 0 and it generates a carry. So how I do that? The carry is put on top of the next digit in number A is, I see here it's 1. Next digit in number B is 0. So here comes 1, here comes 0, and the carry generated from the previous addition is kept on top of it. Then 1 plus 1 plus 0. So again, 1 plus 1 in binary, sum is 0. That's what I keep here. And it generates a carry that becomes another bit to be added to the next addition of number A. So next bit in number A is 0. That comes here. Next bit in number B is 1. That comes here. So finally, I am going to add 1 plus 0 plus 1. So 1 plus 1 again, the sum is 0 and it of course generates the carry. So that carry I put here. The final bit of the 4-bit number in number A is 0. That is kept here. In number B, the final fourth bit is 0. And the 1 plus 0 plus 0, the sum is 1. And of course, there is now no carry. So this number 1000 in binary is 1000 number C, and that is equivalent to decimal 8. So this is how we've seen how the multi-bit binary addition takes place. We got the example of 4-bit addition. We got you the examples of 8-bit addition. Similarly, you can do addition of 16-bit numbers, 32-bit numbers. Their decimal equivalent can be represented, and accordingly, this is how in computers and in microprocessors, the addition, the digital logic addition in binary takes place. So hope you found this model useful. If you did so, share it with others for wider reach. Stay tuned for more engaging content like this. Till then, wish you happy learning.